Today we're going to focus on the celestial sphere and look at how it's used to reference the position of celestial objects for navigation. We're going to cover a lot, so I'm going to leave timestamps in the description below if there are specific points that you're looking for. Before understanding the celestial sphere, it's essential that you understand how to reference positions on Earth. You'll already know that we use latitude and longitude for that. For historical reasons, Greenwich is used as the main origin. If I add this indication line here at Greenwich, we can see how everything relates. The position of this line is approximately 51.5 degrees north, 0 degrees east or west. Travelling north, latitude increases until you reach the North Pole at 90 degrees. Then, going back the other way, latitude decreases until it reaches 0 at the equator, and as you continue further south, latitude starts to increase again until you reach 90 degrees south at the South Pole. If we return to a latitude of 0 degrees on the equator, we can quickly cover longitude. As we move towards the east, longitude increases in an easterly direction. Likewise, if we move towards the west, the easterly figure will then decrease to 0 before increasing in a westerly direction. And as you move all the way around the Earth, you reach a point where longitude becomes 180 degrees west, and this is the anti-meridian, where the longitude could actually be 180 degrees east or west. As you continue further west, longitude jumps to being east and starts reducing until you reach the Greenwich line or prime meridian at 0 degrees again. Of course, you can use this system to map any position on the surface of the Earth, latitude measuring how far north or south you are, and longitude measuring how far east or west you are. But how does that relate to the celestial sphere? Let's make this diagram a little more realistic. If we circle around the planet, you can see that there are different stars in all different directions. All those stars are different distances away, but for the most part they appear to stay fixed for observers on Earth. Of course, in reality, the Earth is spinning, but all those stars still appear fixed relative to the Earth's location. The celestial sphere is just a way to represent all of this. We imagine a sphere larger than the Earth that all the stars are projected onto, and the Earth spins within that celestial sphere. Just ignore the scale here, the celestial sphere should actually be infinitely large. We reference positions on the celestial sphere in the same way we did with latitude and longitude on the Earth. It's all with reference to angles from the centre. But we can't use latitude and longitude because the Earth is not fixed within the sphere, it's rotating. To measure north and south, instead of latitude, on the celestial sphere we use declination. As you move towards the celestial North Pole, declination increases until you reach 90 degrees north, or positive 90. As you move back through the celestial equator, you pass through 0 degrees, and then move towards minus 90, or 90 degrees south declination, at the south celestial pole. The celestial equivalent of longitude, however, is a little more complicated. Remember, on Earth we use that arbitrary line through Greenwich. On the celestial sphere, we need an equivalent arbitrary location to measure from. We use what's known as Aries, or more precisely, the first point of Aries, which is the location of the vernal equinox. Remember that the Earth doesn't actually spin upright. With reference to the plane of the solar system, the ecliptic, everything we've been discussing so far is actually tilted by approximately 23.5 degrees. The Sun, being in the plane of the solar system, follows the ecliptic path around the celestial sphere over the course of a year. The points where the celestial equator crosses the ecliptic are the equinoxes. You get the vernal equinox in the spring and the autumnal equinox in the autumn. Now, when it was first used in this way thousands of years ago, the vernal equinox coincided with the constellation of Aries. The Sun was located within Aries on the celestial sphere on the date of the vernal equinox. This is why the Nautical Almanac refers to Aries as the reference position for all the other stars. They're just meaning a standardised position based on a vernal equinox. In reality, precession over the centuries has meant that the current vernal equinox actually occurs around 30 degrees away from the constellation of Aries. This is why the vernal equinox is known as the first point of Aries. Either way, the first point of Aries nails down a point on the celestial sphere from which we can measure all other stars. Let's pretend this bright point is the first point of Aries for now. All stars are measured in the same direction, and we call this the right ascension. On the Earth you get latitude and longitude, and on the celestial sphere you get declination and right ascension. Looking down on the celestial sphere from the top, right ascension measures anti-clockwise. For navigation and things like the almanac, we actually use sidereal hour angles instead. These are the mathematical complement of right ascension, meaning they measure in the opposite direction. This would be a right ascension measure, and this would be the equivalent sidereal hour angle. So, now we've seen how to locate bodies on the celestial sphere with declination and right ascension, how to locate positions on Earth with latitude and longitude, the only point left to cover is how to locate celestial bodies with reference to an observer on the surface of the Earth. Let's take an observer on a ship here in the middle of the Atlantic Ocean. I'll add in the celestial sphere as well. Again, this is only going to be a partial sphere so that we can still see what's going on. From the ship, you obviously can't see the entire celestial sphere. You can only see a partial one. You can actually see pretty much half of the actual celestial sphere. The diagram is a bit harder here because the celestial sphere should be infinitely larger than I've drawn it. The area that you can see is centred on your zenith. The zenith is just the point on the celestial sphere straight above you. The actual hemisphere of sky that you can see is just the hemisphere centred on that zenith. It's 90 degrees in all directions. Obviously part of mine is cut away here. The final label that we need is the horizon. And the horizon is the line where your hemisphere of sky joins the visible surface of the Earth. When we talk about horizons, there are actually a few different horizons depending on height of eye. You get the celestial horizon, which is 90 degrees from your zenith, which is the bottom of that dome we've just covered. And you get your true horizon, which is based on height of eye and the curvature of the Earth. In general, we don't worry too much about the difference for maritime navigation because the two are so close together, and any bodies close to the horizon are no good for navigation anyway. Finally, to locate stars on your own dome of sky, we use local measures instead of the global measures of declination and right ascension that we've already covered. Logically, all you want to know is what way to look and how high to look. The bearing of a body from you is known as its azimuth. This just tells you what way to look and is given as a compass bearing. For example, the pole star will have an azimuth of pretty much 0 degrees, meaning you need to look in a northerly direction to see it. And lastly, how high the star is. We use the altitude of the star, which is its height above the celestial horizon. The mathematical complement that you will sometimes see is the zenith altitude, and that is just measuring from the zenith to the body, and will be 90 degrees minus the body's altitude. Again, imagine the pole star. If you're stood at the North Pole, it would be right above your head, on your zenith, at an altitude of 90 degrees. If you move to the equator, it would then be right on the edge of your own hemisphere of sky. Its altitude would be pretty much 0 degrees. As a side note, notice how those altitudes of the pole star just happen to match the latitude of the observer. You need a little more calculations for accuracy, but that is the principle of finding your latitude by Polaris. So, to sum up, we've looked at latitude and longitude, declination, right ascension and sidereal hour angles, the zenith and the horizons, and now altitude, zenith altitude and azimuths. Hopefully when you look at these diagrams of celestial navigation, they'll start to make more sense. Anyway, until next time, thank you for watching, and goodbye.